Kind of wonky on me here. All right, so hopefully this will be okay. All right, so there we've got that first reaction. We've written it in the reverse direction, and now we can just write the K the way we normally would, because that would be the K for the reverse direction. So our Kc would be equal to concentration of CH4 squared, concentration of O2 cubed, over concentration of CO squared times concentration of H2O raised to the fourth. All right, we'll see if it keeps going on this one here. So, all right. Let's see, number 15. Okay, so magnitude of Kw. So we know what Kw is, right? So Kw is the equilibrium constant for our reaction that goes like this. Two water molecules colliding together to give us H3O plus and OH minus. Okay, so we have an equilibrium constant that's equal to concentration of H3O plus times concentration of OH minus, and we know that it has a value of 1 times 10 to the minus 14. Okay, it's a very small value. So what does that small value of Kw tell us? Okay, it tells us that this reaction goes very little towards the product side. So it auto-ionizes very little. Okay, most of what you have in water is still water molecules completely intact. You have a little bit of H3O plus and a little bit of hydroxide. That's it. Okay, so that's why the answer there is E. Questions on that one? Okay, how about 16? Yes? Okay, so we want to know what's the pH of an aqueous solution where the OH is 0.0025. Okay, so we know that our OH concentration is equal to 0.0025 molar. So with that, we can calculate a pOH. There's a couple different ways to calculate this one. We can do a pOH. Remember, pOH is just equal to negative log of the OH. Okay, so your pOH would be equal to negative log of 0.0025. So that gives us a value of 2.60. And then we also have the relationship that the pH is going to be equal to 14 minus the pOH, because the pH plus the pOH have to equal 14. So we have 14 minus 2.60, and that gives us 11.40 for the pH. Okay, questions at all on that one? Any questions there? Okay. Let's see. How about 17? Yeah? Okay, so 17 just kind of goes back the other direction. It says, what is the concentration in molarity of hydronium ions in a solution with a pH of 4.282? So, concentration of hydronium ions is just the reverse of our pH equation. So that's equal to 10 to the minus pH. So that's going to be equal to 10 to the minus 4.282. We got to wake up. Sorry. So you got 4.282, and when you plug that into your calculator, you get 5.22 times 10 to the minus 5. And that's going to be a molarity. Any questions at all on that one? Okay. See, that was a better statement we can't see than what they asked last time and said, can you lift that up? I just did this. Yes, I can. I took my vitamins. All right. Where are we at? Number 18. Yep. All right, calculate the concentration in molarity of hydronium ions in a solution with a pOH of 4.223. Okay, so again, there's different ways that you can work these pH problems. You can work them strictly from a concentration standpoint with kW, or you can use pOHs and pHs, and there's just lots of different ways that will get you to the same answer. I like using the pHs and pOHs. So we know that our pOH here is equal to 4.223. Okay, so I know that my pH is going to be equal to 14 minus 4.223. Again, the pH plus the pOH of a solution is going to be equal to 14. And so my pH ends up being equal to 9.777. So now that I know my pH, it wants my hydronium ion concentration. Well, we just saw that on a previous problem. That's equal to 10 to the minus pH. So that's 10 to the minus 9.777. And that works out to be 1.67 times 10 to the minus 10. Okay. Everybody good with that one? Questions at all? All right. Anybody going to the career fair tomorrow? No? No. I just thought I would as a courtesy to her. So, she runs it. So, there's a lot of good internships out there. That's why I wondered. But I know having it the same day as the test is that's just bad luck. So, but if you're looking for an internship, that's a great place to go because there will be a lot of folks there looking for internships. All right. Number 19. Yeah? Okay. So conjugate base of HSO4 is. So again, this is kind of an interesting question. You've really got to think about what it's saying. It says the conjugate base of HSO4. So if we're looking for the conjugate base of HSO4, that means that HSO4 is acting as a what? It's acting as an acid, okay, because acids have conjugate bases. So we've got to read that one very carefully. So HSO4 plus water then is going to form, if it's acting as an acid, it's going to give us H3O plus, and then it's going to form SO4 2 minus, and so my conjugate base for HSO4 is my SO4 2 minus, that sulfate ion. Okay, it's not something you can it's not something you can memorize, not something you can look at. You've really got to read that and say, okay, what is it telling me? What information did it give me in that statement? Okay, and it told you that it was acting as an acid. Very good. Number 20. Oh yeah, 20. Woo, yeah, 20. Woo. 20 is kind of a weird one. It's kind of a weird one. But the thing you've got to remember is that we've been dealing with a KW always at 25 degrees Celsius. Everything that we do has been around 25 degrees Celsius. The pH scale with a neutral at 7, that's based on 25 Celsius. pOH and pH equaling 14, that's based on a 25 degrees Celsius. As soon as you change the temperature and change the K for water, you change that KW, all that other stuff goes out the window. So if you're going to work in any kind of, like if you're going to do geology, like down in Yellowstone where you've got, 200 and some degree water, the Ks are going to be very different in that hyper heated environment. So, just something to keep in mind. But this one, we're just looking at water at 50 degrees Celsius. And so that kW here is equal to 5.47 times 10 to the minus 14. Okay, so it dissociates better. It has a K that shifted more towards the product side there. So remember my kW reaction, this hasn't changed. It's H2O plus H2O goes to H3O plus OH minus. And again, our kW is going to be equal to concentration of H3O plus times concentration of OH minus. And if you went through and you did an ice box, all you would have is an X and an X for the H3O plus and the OH minus. And so for this problem, what you would end up having is 5.47 times 10 to the minus 14 is equal to X times X. So that's equal to X squared. So when you take the square root, you get X equaling something I can't read on my own handwriting. Looks like 2.34. There we go. 2.34 times 10 to the minus 7. Okay, so that's equal to the concentration of the H3O plus at this temperature in pure water, and it's also equal to the concentration of OH minus at this temperature. So those two things are still going to be equal to each other. They're just not going to be 1 times 10 to the minus 7. Okay, so this is going to be equal to concentration of H3O plus, and so my pH becomes a negative log of 2.34 times 10 to the minus 7, and that equals 6.63. Now here's kind of the question, is that acidic or basic? It's neutral. It's neutral. That's the new neutral at that temperature. And it's because the pH scale goes out the window. That neutral point at 7 is for 25 degrees Celsius, but as soon as you change the temperature, that goes away. It all changes because the kW changed. Okay, so that pH of 7 in neutrality is based on that kW being 1 times 10 to the minus 14. As soon as that kW changes, your whole pH scale changes. Okay? It is definitely more acidic than it was at 7 because it has a higher concentration of H3O plus. It also has a higher concentration of OH minus too, and they're still the same, which is why it's neutral. Does that make sense? I mean, it's not a huge deal, but it's a good concept to understand. Deepens your understanding. All right. Number 21. Yes, I'm probably working the rest of them out, so you should probably just stop asking. All right, so 21 is phenol. And so it says phenol is a weak acid. There's a clue. It's a weak acid that's used as a disinfectant. The Ka is 1.3 times 10 to the minus 10. We want to know what is the pH of a 0.025 molar solution of phenol. Okay, so I did my icebox here, or my reaction. I just put HPH for phenol. It's an acid, so I just put an H on it. It doesn't really matter what the formula is. I'm going to put that in water. And because it's an acid, it's going to lose an H plus, and it's going to give it to water, and I'm going to have H3O plus. So we can icebox this. So my initial concentration of phenol is 0.025. I've got none of either of those. I don't care about the water. I'm going to lose some of that. I'm going to gain some of that. I'm going to gain some of that. So I end up with 0.025 minus X, X, and X for my equilibrium concentrations. Okay, so we can set up our Ka, which is going to be equal to the concentration of the pH minus times concentration of the hydronium all over concentration of the original acid, my phenol. Okay, so that's got to be equal to my Ka value, which is 1.3 times 10 to the minus 10. So that's going to be equal to X times X over 0.025 minus X. Okay, so very small K. So I'm going to take that X, I'm just going to throw it out. It's going to be really small. Okay, that really tiny k, remember what that means? It means that that reaction moves a very tiny amount in the forward direction. And because of that, I know that my value of x is going to be small because that's the only place x is getting made is by the forward reaction. I'm guessing it's going to be a lot smaller than 0.025. So that simplifies my equation to 1.3 times 10 to the minus 10 is equal to x squared over 0.025. And then when I solve for x, which is equal to the concentration of H3O plus, I get a value of what? 1.80 times 10 to the minus 6. Okay, and when I take the pH of that, or the negative log of that to get the pH, I get a pH of 5.74. Okay, and if you take this value for x, this 1.8 times 10 to the minus 6, you divide it by the 0.025 and multiply by 100. That'll tell you what percent of it that is. And as long as that's lower than 5%, then you were okay ignoring that x. And I can do that by inspection. That's going to be a lot smaller because it's about 1,000 times smaller. Okay, this ignoring of x isn't a chemical thing. It's a mathematical thing. It's just making life easier is all we're doing there. We're making an estimate, making the calculation easier. It's the only reason we do it. We're not doing any special thing for the chemistry equation. We're just trying to make the math a little easier. Okay, we introduce a little bit of error, but it's acceptable. Okay, that's what we're doing when we're ignoring x. All right. Number 22. Yeah, 22, very similar to a problem I worked out in class. Okay, so let's see, we've got a 0.058 or 578 molar solution of a weak acid. It's got a pH of 2.29. What is the Ka? So we've got some acid here. I'm just going to call it HA. I'm going to put that into water. And it's going to dissociate into H3O plus A minus. Doesn't really matter what the acid is, it's just some acid, okay, with an H on it. So we're going to icebox that. I know I start with a solution of 0.0578. None of that and none of that. That's all before it's dissociated. Okay, now we let it dissociate. We're going to lose some of it. When we lose it, we're going to gain some H3O plus. We're going to gain some A minus. So we have 0.0578 minus X for equilibrium there, X and X. Okay. So we set up our Ka. That's going to be equal to our X times X on the top, so X squared. I'm just trying to save a little space here. Down here, 0.0578 minus X. Now normally at this point, we would solve for x, but we can't do that here because we don't know the Ka. That's what we're looking for. Okay, but we can find that value of x, and the reason we can find x here is because we were told that the pH is 2.29. And so x represents the concentration of H3O plus, and I can find the concentration of H3O plus because I know the pH. So I know that my concentration of H3O plus is going to be equal to X, which is going to be equal to 10 to the minus pH, which is 2.29. So my value for X here becomes, I've got to find that on my sheet here, 5.13 times 10 to the minus 3. Okay, 10 to the minus 3. So now I can take that value of x right here, and I plug it in to x squared. I plug it in here to this x. Now, something a lot of people did was they ignored this x down here, but don't do that. If you know what the x is, don't ignore it. Okay, and actually, if you do a quick calculation on here, you'd probably find you can't because it's about 10% of that value there. So there's no way you can ignore the x anyways. But if you know the x, don't ignore it. It's always more correct to include it if you can. Okay? So when you plug in that value for x in all of those different places, you end up with a Ka of what did I get? 4.99 times 10 to the minus 4. Okay, questions at all on that one? Any questions there? Doing good on time. All right, 23. Yes? Okay. So for number 23, we've got the Ka for HCN is 4.9 times 10 to the minus 10. So Ka, that doesn't help me very much. Sorry. It's just too easy. Like I said, this is why my wife in the middle of the weekend says, "Don't you have a class to teach?" Wish I had a nickel for every time I heard that. So, I'd be a rich man. I wouldn't have to teach. So, Ka is 4.9 times 10 to the minus 10. What we're looking for is the Kb for our Cn minus. We don't know that. So what do we notice about HCN and Cn minus? They represent a what? Conjugate pair. They are a conjugate pair. And we know that because they differ by an H+, just one H+. If you have two compounds that differ by one H+, they're a conjugate pair. And what we know for conjugate pairs is that the Ka times the Kb has to equal Kw. Okay, so we know the Ka. We're looking for the Kb, so the Kb is going to be equal to the Kw divided by the Ka. So that's 1 times 10 to the minus 14 over 4.9 times 10 to the minus 10. And when we work that out, we get 2.04 times 10 to the minus 5. Okay, questions at all on that one? Yes?
So that's Kw, tell us otherwise.
Yeah, that's the Kw at 25 degrees Celsius. So yeah, if it doesn't tell you, if it doesn't say anything else about temperature, just assume that one. Yep.
Moving on with the next question, how come the Kb on number 24 is reported differently from the one we just calculated?
I have no idea. They really messed that one up. I noticed that today as well.
Because like the answer key, it matches up if you use the number that's given in the problem, but it's...
I know. I didn't write it, so I can't help you on that one. But yes, I saw that one today, and I'm going, that doesn't make any sense at all. Somebody screwed up. But yeah, just work the numbers as they're given to you. But I would agree, they screwed something up. All right, number 24. Yes, okay. So as was just mentioned to me, and I noticed this earlier today, and I thought it was kind of funny. So it says the Kb for Cn minus is 4.9 times 10 to the minus 10. Well, that's what we just calculated in the previous problem, 2.04 times 10 to the minus 5. What the hell? Yeah. So I think they screwed something up. Because they actually reported on 24 that I think the 4.9 times 10 to the minus 10 actually is the Ka for HCN. That's an appropriate value. So I think that's what it was supposed to be, was the Ka for HCN on problem 24. But we'll just work it the way that they wrote it, because when you work it the way they wrote it, you get the answer that they say it is. So, but they screwed it up. They really did. So we want to calculate the pOH. For an aqueous solution of sodium cyanide at 25 Celsius, the Kb is that value there. So we know that Cn minus is the conjugate base of HCN. So HCN is a weak acid. Cn minus is its weak conjugate base, which means it's going to behave as a base in solution. It's going to react with water in equilibrium, and it's going to take a proton away. So, because that's what bases do. So it's going to form HCN plus OH minus. We're going to icebox this. Okay, we had a sodium cyanide solution, so it's a sodium salt. It's going to completely break apart. I know it's 0.0827 molar to start with. I've got no HCN and no hydroxide. I'm going to lose X of my cyanide. It's going to make X amount of HCN and make X amount of OH minus. It's going to have 0.0827 minus X, X, and X. Okay, so now when I work this one out, because this is a base reaction, it has something taking an H plus away from water. I'm going to write it as a Kb. Okay, so that's going to be concentration of HCN times concentration of OH minus over concentration of CN minus. So that's going to be equal to X times X over 0.0827 minus X. That's got to be equal to 4.9 times 10 to the minus 10, because they told us that was the Kb, so we don't have to do any converting there. And because that's such a small K, we're going to ignore that X, and we're going to work out a value for X here from the ones on the top, and we end up with an X value of 6.37 times 10 to the minus 6. Now it's important to go back to the icebox and see what X is equal to. One of the things that we see X is equal to is the concentration of OH minus, because we have OH minus in our icebox. So all we need to do, the problem asks for the POH. So the POH is going to be equal to the negative log of the OH concentration. So that's negative log of 6.37 times 10 to the minus 6, and that comes out to be 5.20. Any questions at all on that one? We got like 5 minutes left. We'll see if we can pound through this one. 25. Yeah! 25 is not too much different from 24. Determine the pH of a 0.15 molar aqueous solution of KF. And hydrofluoric acid, it gives you a Ka. Okay, that's pretty typical of how these kinds of problems are going to go. You're given a salt, okay, so Kf, so that's going to break apart into K plus and F minus. Okay, that's step one. Got to recognize you've got a soluble salt that's going to completely break apart. Next thing you've got to realize is that this is the conjugate base of a weak acid. And because of that, it has base properties in water. So it's going to react with water in an equilibrium. So we're going to have F minus plus H2O. That's going to go to HF plus OH minus. Okay, it's going to take an H away. Because that's an equilibrium, anything weak forms an equilibrium. So we can icebox that. I know I'm going a little fast here, but just want to make sure I get out of here on time, because Dr. G's coming in for 121. So we got 0.15. We're going to lose some of that to get to equilibrium. We're going to gain some of that. We're going to gain some of that. So we get 0.15 minus X, X, and X. So this is a Kb reaction because it's got it reacting as a base. So that's going to be X squared. That's my HF times OH over my F minus. So 0.15 minus X. Okay, and once again, we have a Kb that we don't know, and we have an X that we don't know. So we've got two unknowns, one equation. Can't solve that. But we can find the Kb, because we know the Ka of the conjugate acid of F minus, of its parent acid. We know that it's HF, and we know it has a Ka of 7 times 10 to the minus 4. So I know that Ka times Kb is equal to Kw. So my Kb is going to be equal to 1 times 10 to the minus 14 over 7 times 10 to the minus 4. And we get a Kb that's equal to 1.4, 3 times 10 to the minus 11. Now I can plug that in here. And then we start solving for x. We can take this x that's here, throw it out because that K is so small. We solve for x that's also equal to the OH minus concentration based on my icebox. And that gives us 1.46 times 10 to the minus 6. So I do a pOH calculation for that. I take the negative log, and I get 5.83. And I subtract that from 14 to get a pH. And that gives me 8.17 on that one. Whew. Okay, so that's how you do that calculation. And in the last minute, I'll do 26. 26 is tricky. I try not to be this tricky. It says if an equal number of moles of the weak acid HF and a strong base KOH are added to water, is the resulting solution acidic, basic, or neutral? No. I have the same number of moles of acid and base. They are going to neutralize each other regardless of their strength. So it's neutral. Oh, no, it should be... oh, wait, yes, it will be basic. Sorry. My bad. So, here's what I missed because I was trying to do this one on the fly. I actually have basic written down. So the OH and the H do neutralize each other, but then you're left with F minus, and that will undergo this reaction that I just did and give you a basic solution. Screwed that one up. All right, guys, thanks so much.